My name is Joanna Boyer, and this is a presentation for Harvard course CSCI-E89 Deep Learning. My topic is a case study in finance, in which I explore the use of variational autoencoders to generate simulation paths for financial time series. The main goal of the project is to simulate patterns that are similar but not identical to historical realizations. Having good simulation scenarios that cover relevant potential future realization of various stochastic processes is of great importance across many areas in finance, including valuation, risk management, testing and analysis of portfolio behaviors, and trading strategies. Backtesting is commonly used to analyze performance on historical data. A common mistake is to rely entirely on backtesting, meaning to demonstrate that a strategy performs well on a selected time interval in the past by replaying history. As we all know, history hardly ever repeats itself, and so it is important to have a set of testing scenarios that capture a richer set of possible market evolutions beyond what happened in the past. The data set used in this illustration was downloaded from the Federal Reserve Bank of St. Louis and pertains to the U.S. 10-year swap rate time series between July 2000 and October 2016. The rate is available as a daily observation for each business day in this interval. There are roughly 4,000 observations in total, and an interesting feature of financial time series in general is that the amount of data available per series when daily or coarser observations are used is actually relatively small compared to the millions of samples available to train deep learning networks for other types of applications. For the purpose of this analysis, I worked with daily changes in the 10-year rate, which I have aggregated into weekly runs of 5 business days each. The idea is to learn such weekly patterns to synthesize paths that are similar to the historical realization. In addition to learning patterns for the full data set, I also explored the ability to generate patterns for prescribed market regimes, such as high rate, high volatility, low rate, high volatility, and so on. To designate high or low, I use the average rate and the average volatility over the entire period as thresholds. Regimes are labeled 1 through 4, and the label has been added as the last column in the input data. A 5th regime has also been included for the weekly runs to characterize the weeks in which at least one regime switch occurs. For the purpose of this presentation, however, the main 4 regimes are primarily illustrated. Variational autoencoders belong to the class of generative models, which in turn constitute a broad area of machine learning dealing with models of distributions of points in potentially high-dimensional spaces. In this case, I explore weekly patterns, which are samples in 5-dimensional space, but longer sequences could be explored and the dimension of the input space would increase accordingly. Variational autoencoders seem like ideal candidates to synthesize latent distributions of financial time series. A typical variational autoencoder is defined in terms of a pair of models, an encoder and a decoder, as well as a loss function. The encoder takes the input, in this case a weekly run, which is a sample in 5-dimensional space, and outputs an encoding of this point into a latent representation space, which I chose to be 2-dimensional in my work. In the case of the variational autoencoder, the latent space is stochastic, and the encoder actually outputs parameters of a distribution, Gaussian in this case, from which we can later sample to generate new weekly runs. The decoder generates a latent vector by sampling from the distribution and then proceeds to develop a reconstruction of the original input. The loss function being optimized during training consists of 2 parts, a mean squared error term that quantifies similarity to the input in L2 norm, and a Kullback-Leibler divergence component that quantifies similarity in distribution between the input samples and the generated ones. One shortcoming of vanilla variational autoencoders is that they offer little or no control over the data generation process. This is problematic if we want to generate specific types of samples, like for instance ones that correspond to a high rate, high volatility market regime and none other. To solve this problem, conditional variational autoencoders were introduced to model latent variable distributions conditional on other random variables like regime type. In this case, the regime labels can be used for this purpose. For this work, I modified the variational autoencoder that comes with the Keras documentation to work with weekly run samples and to add conditioning on market regime as previously described. Let's have a look at the code. First, we import the necessary modules, including Keras, NumPy, and Matplotlib for visualization of results. Next, we load the data from the CSV file into arrays, which are then fed as inputs into the train test split function to separate training from validation data. We can actually visualize what the data looks like. In green, we have the time series of the daily changes in the 10-year swap rate, and in orange, we have the regimes as coded by their levels, 1, 2, 3, 4, shown on the right axis. For example, the beginning period, starting in July 2000, is a period of relatively low volatility when rates are high, so the corresponding regime is 3. This is followed by regime number 1, then briefly reverting to 3 before returning to 1, so on and so forth. Next, the autoencoder is built inside the build models function. As already explained, it consists of an encoder piece, a decoder piece, and a loss function, which itself has two parts, the mean square error and the Kullback-Leibler divergence part. Finally, we are ready to train the model. In this case, it has already been trained to avoid waiting during the video recording. But basically, for each regime, we can see the training epochs. We can see the parameters of the corresponding latent distribution. We see some newly generated samples, as well as training and validation loss graphs. Different regimes show different patterns of newly generated samples, which seems to indicate that our assumptions that the regimes are distinctive and that distinctive features can be learned for each one of them is on the right track. Finally, we can plot some more results. In this case, we can see all the regimes plotted together as distributions in latent space. The top one is for the mean, the bottom one is for the latent log variance. We can also display some weekly segments around day 3500 in the data series. This timestamp was randomly picked for illustration. The actual historical path is shown in red, and the new paths are shown in blue. And finally, we can use these new paths to synthesize full paths. One challenge is to constrain the full path to stay relatively close to the historical one, or to stay between economically meaningful limits. It should not reach extremely negative or extremely high levels that are practically unobservable in reality. To enforce such properties, I introduce a similarity interval parameter, which is expressed in the number of days that a new path can freely evolve before it's constrained to return to the actual. And some results are shown here. Again, the historical path is shown in red, and 50 paths that have been newly generated are shown in blue, and we can see how these paths are different from the historical path and yet follow it closely. In conclusion, variational autoencoders show good promise for the synthesis of simulation paths. However, more work is needed to better quantify generated path properties and to enforce global constraints. The appeal of using variational autoencoders lies in the fact that they are capable of uncovering latent probabilistic parameterizations automatically. They also offer several avenues for further exploration, as they can be extended to work with different families of distributions, and they can also be adapted to higher dimensional inputs, biweekly or monthly, for example. The main drawback, as identified so far, lies in the difficulty to aggregate patterns into full paths while obeying global constraints.